Howdy. We can start by asking a question, can a compound act like an acid when it reacts with one compound and behave like a base when it reacts with another? And the interesting answer is yes. And so if a compound reacts with a stronger base, then it can behave like an acid. If it reacts with a stronger acid, then it can behave like a base. And so this video is on Bronsted-Lowry theory of acids and bases and conjugate acid-base pairs. And so it's important because all buffers and indicators are composed of conjugate acid-base pairs. If you know the Ka of an acid, you can actually calculate the Kb of its conjugate base. And if you know the Kb of the conjugate base, you can calculate the Ka of the conjugate acid. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. Now, here I'm saying that acid and conjugate base, and here base and conjugate acid. It's actually acid-base conjugate pair. And so a base will always have a conjugate acid, an acid will always have a conjugate base. But again, think about it in terms of an acid-base conjugate pair. And so after watching this video, you should be able to determine if a compound is behaving like an acid or a base. You should be able to identify the conjugate bases of acids and the conjugate acids of bases. Given the Ka of an acid, you should be able to calculate the Kb of its conjugate base. Given the Kb of the base, you should be able to calculate the Ka of its conjugate acid. And you should be able to determine if a compound is a strong acid, strong base, weak base, or neutral, based in part on conjugate relationships. And so there's three common acid-base theories: Arrhenius theory, Bronsted-Lowry theory, and Lewis theory. And when we're characterizing something as being a strong acid or strong base, we're using Arrhenius theory. If you add it to water, it produces hydrogens, it's an acid. You add it to water, it produces hydroxide, it's a base. Now, Bronsted-Lowry theory and Lewis theories are a little bit different. They're looking at how is something behaving like in a reaction. And so if in a reaction something donates a hydrogen, then it's behaving like an acid. If in a reaction it accepts a hydrogen, then it's behaving like a base. For Lewis theory, if in a reaction it accepts the electron pair, then it behaves like an acid. If in a reaction it donates the electron pair, it behaves like a base. Remember, these two are consistent, but the Lewis theory is more general. And so if we look at the reactions below, here we have ammonia plus water forming ammonium ion plus hydroxide. And so the ammonia is going to accept the hydrogen ion. And so we'd say the ammonia is behaving like the base. The water is donating the hydrogen ion, and so the water is behaving like the acid. Now if we look at the second reaction, HF plus water goes to F minus plus hydronium ion. And so the HF is losing its hydrogen ion, and so it's behaving like an acid. And then water's accepting the hydrogen ion, and so it's behaving like a base. And so in the top reaction, the water's behaving like an acid. In the bottom reaction, the water's behaving like a base. And so whether or not water behaves like an acid or a base just depends on what it's reacting with. If it reacts with something that's a stronger base, then the water behaves like an acid. If it reacts with something that's a stronger acid, then the water behaves like a base. And so we're using Bronsted-Lowry theories, acids and bases, to identify the acids and base. And now it's kind of interesting, if we look on the product side, and imagine the reaction going backwards, we'd see here that the ammonium ion is going to lose a hydrogen ion, and so it's behaving like an acid. And the hydroxide ion is going to accept that hydrogen ion, and so it's behaving like a base. And so typically for acid-base reaction, you can think about going forward, and you'll have an acid and a base. And then if you think about the reaction in reverse, you also will have an acid and a base. Now if we look at the ammonia and the ammonium ion, that's a conjugate pair. Conjugate pairs differ by one hydrogen ion. Right? So if we take ammonia and we add a hydrogen ion, then that gives us the ammonium ion. If we take water, remove a hydrogen ion, that gives us hydroxide, and so that's another conjugate acid-base pair. And so a conjugate pair differ by one hydrogen ion. And so if you take the acid, if you remove the hydrogen ion, that gives you the conjugate base. If you take the base and you add one hydrogen ion, that will give you the conjugate acid. And so again, think about them as pairs. They're conjugate acid-base pairs. And again, it's kind of interesting. Depending on what's reacting with, water can be an acid or a base. Bicarbonate can behave like an acid or a base. Hydrogen sulfate can behave like an acid or a base. And so if we think about the ammonia-ammonium ion conjugate pair, for the ammonia, it's our typical weak base. It reacts with water, forming ammonium ion and hydroxide ion. You have hydroxide as a product, so we think about that as a Kb. The Ekman constant for this reaction is Kb for ammonia. Now here we have the ammonium ion forming ammonia plus hydrogen ion. Again, if you see hydrogen ion as a product, we think Ka. And so the Ekman constant here is the Ka for the ammonium ion. Now if we add these two reactions, so the ammonia plus water gives an ammonium ion, gives us the ammonium ion plus hydroxide plus ammonia plus hydrogen ion. Remember, things common on both sides cancel. So the ammonium ion cancels the ammonium ion, ammonia cancels ammonia, and then we're left with water going to hydrogen ion plus hydroxide ions. Now you should recognize this as having an Ekman constant equal to the Kw. Now you should also remember that when you add reactions, you multiply the corresponding Ekman constant. And so that tells us that, well, this has the Ekman constant of Kw. It should also have the Ekman constant of Ka times Kb. And so for a conjugate acid-base pair, Ka times Kb equals Kw. So Ka of the acid times Kb of its conjugate base will equal the Kw. Now this is really helpful for a couple of different reasons. One, it tells you that the stronger the base, the bigger your Kb, the weaker the acid, the smaller your Ka. And the stronger the acid, the larger the Ka, the smaller the Kb. And so the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. And so Ka, Kb, pKa, and pKb are all related. Given one, you should be able to determine the other three. And so we saw Kw equals Ka times Kb. Now if we take the minus log, we get minus log Kw equals minus log Ka times Kb. Remember, log of A times B is equal to log of A plus log of B. And minus log of Ka is our pKa. Minus log of Kb is our pKb. And so we end up with pKw is equal to pKa plus pKb. And so again, all four of these are related. Given one, you should be able to determine the other three. And so if we're given the Ka, to get the pKa, we just take the minus log. So Ka of 10 minus 13 gives us a pKa of 13. To get the pKb, remember pKa plus pKb equals pKw. And at 25 degrees Celsius, pKw is equal to 14. And so if our pKa is 13, that means our pKb would be 1. And then for our Kb is going to be equal to it's going to be equal to 10 to the minus pKb. And so if our pKb is 1, that gives us Kb is 10 to the minus 1. And so this looks very similar to when we talked about pH, pOH, hydrogen ion concentration, and hydroxide ion concentration. Given one of those, you should be able to determine the other three. And again, same thing, given one of these, you should be able to determine the other three. Also, again, notice that in some cases, the step is single. So if you want to go from Ka to Kb, remember Ka times Kb equals Kw, and so Kb equals Kw over Ka. But sometimes if you want to do like from Ka to pKb, that's going to be a two-step process. So first you have to do the Kb, and then remember that pKb is just equal to minus log of the Kb. But again, very, very similar to when we talked about pH, pOH, hydrogen ion concentration, and hydroxide ion concentration. And so here we have the base has a Kb of 5.6 times 10 minus 4. And its conjugate acid is going to be, we just add a hydrogen ion. Now, what is the Ka of the conjugate acid? And so we just saw that Ka times Kb equals Kw. And so that means that the Ka is going to be equal to Kw over Kb. And again, remember, this equation is only for conjugate acid-base pairs. And so our Kw is 10 to the minus 14th. Again, if you're not given the temperature, assume 25 degrees Celsius. Divide out by our Kb, which is given as 5.6 times 10 to the minus 4th. And so that gives us a Ka of 1.8 times 10 to the minus 11th. Now here we have a table of acids. These are actually all weak acids. Remember, the Kas for a strong acid can be treated as an infinite, but they're like 10 to the 9th. And so of the acids on the left, which is the strongest, and so Ka is used as our indicator of the strength of the acid. And so the strongest acid should be that top one. And the weakest acid should be that bottom one, because this table is in order of the Ka. Now, a kind of interesting question is we can look at the conjugate bases of these acids, right? So if we remove the hydrogen ion, then we're left with IO3 minus. Remove the hydrogen ion, the first one we have H2PO4 minus. Now, of these bases, which is going to be the weakest? And so we saw that this was the strongest acid, and so that means this would be the weakest base. The stronger the acid, the weaker the base. And so IO3 minus is the weakest base in this column, and CN minus is is the strongest base. So the weaker the acid, the stronger the base. The stronger the acid, the weaker the conjugate base. And so again, we have some bases, and this time we have KBs. Again, they're in order. And so the strongest base on this table should be that top one. And then the weakest base in this table will be that bottom one. Now, again, we could look at the conjugate acids. So remember, if I want to go from the base to the conjugate acid, we add a hydrogen ion. And so we've added this hydrogen ion. And make sure you look and make sure that the charge changed, right? We went from charge neutral to having a +1 charge. We went from charge neutral to a +1 charge because you're adding a hydrogen ion. Now I could ask, of these acids, which is the strongest acid, which is the weakest acid? So we saw that this was the strongest base, and so that would mean this is the weakest acid. This was the weakest base, and so that would be the strongest acid. And so Ka times Kb equals Kw. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. Now we can actually make a table of acidic, basic, and neutral, of cations and anions. And so the ones in blue are just the conjugate relationships. And so conjugate acids of weak bases are acidic. Conjugate bases of weak acids are basic. Now this one's kind of interesting. Conjugate bases of strong acids are actually neutral. So a strong acid is so strong that their conjugate bases are neutral. Now we can add a couple more things to this table. So hydrogen sulfate and dihydrogen phosphate are acidic. Small highly charged metal ions are acidic. Alkali metal ions and alkaline earth ions are neutral. And so it's kind of cool. We can use this table to actually determine if a solution is acidic, basic, or neutral. So for instance, here we have potassium iodide. Is a potassium iodide solution acidic, basic, or neutral? And so potassium ions are alkaline metal ions, and so that would be neutral. And iodine is the conjugate base of a strong acid, and so that would be neutral. And so both potassium ions and iodine ions are neutral, and so potassium iodide solution would be neutral. Now here we have potassium nitrite. Now you got to be careful. The nitrite is the conjugate base of a weak acid, right? Nitrate is NO3 minus. That's the conjugate base of a strong acid. Nitrite has 2 oxygens. That's the conjugate base of a weak acid. And so the potassium, again, is neutral. The nitrite ion is actually basic because it's the conjugate base of a weak acid. And so a solution containing potassium nitrite would actually be basic. And so our conjugate relationship Ka times Kb equals Kw for acid-base pair. And again, that gives us the blue. And so we can use this table to determine if a solution is acidic, basic, or neutral. I hope that was helpful.